Substitution with inverse trigonometric functions. Okay, let's begin with slide 1. Welcome. This slide marks the beginning of our exploration into using substitution with inverse trigonometric functions. Now, in the sections we've covered previously, we established a really important idea when it comes to choosing the right substitution technique for integration. Remember, the most effective strategy is to look for a portion of the integrand. That's the function inside the integral, whose derivative is also present within the same integrand. This principle isn't limited to just polynomial or exponential functions. It applies perfectly to inverse trigonometric functions as well. What are inverse trigonometric functions? These are functions like arctangent of x, or inverse tangent of x, and arcsine of x, or inverse sine of x. They frequently show up in integrals, and crucially, they often appear together with their derivatives. Think of it like spotting a matching pair. When you can identify these pairs, the inverse trigonometric function and its derivative, within an integral, you've unlocked a powerful simplification technique. You can often transform what looks like a complicated integral into something much more manageable, something you can solve using basic integration rules, like the power rule, simply by changing variables. So, that's the core idea we'll be building on in the following slides. We'll learn to recognize these pairs and then systematically apply substitution to solve these integrals. The core concept, identifying the pairs. First, it's crucial to remember their derivatives. You absolutely need to be comfortable with what you get when you differentiate inverse tangent, inverse sine, and inverse cosine. This isn't just memorization, it's about recognizing patterns. The goal here is to think of these functions and their derivatives as a package. When you see one, immediately look for the other. If you spot that pairing, it's a strong signal that substitution will simplify the integral. Now, let's look at the most common pairings you'll encounter in grade XII mathematics. Number 1, if your integral contains inverse tangent of x, that's arctangent of x. Keep an eye out for the term 1 over 1 plus x squared. Remember, the derivative of inverse tangent of x is 1 over 1 plus x squared. So, if you see both of those together, that's a perfect setup for substitution. We'll let t equal inverse tangent of x, and that will allow us to simplify the integral. Next, if the integral contains inverse sine of x, or arcsine of x, look for the term 1 over the square root of 1 minus x squared. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Therefore, if you see both of these, you can substitute by letting t equal inverse sine of x. Finally, we have inverse cosine of x, arc cosine of x. This one is a little tricky. If you see inverse cosine of x, look for 1 over the square root of 1 minus x squared, but pay attention to the sign. The derivative of inverse cosine of x is negative 1 over the square root of 1 minus x squared. So, when you make the substitution, letting t equal inverse cosine of x, you need to remember to account for that negative sign. Okay, so let's move on to slide 2. As we discussed on the previous slide, the key to successful substitution is identifying a function and its derivative within the integral. This slide focuses specifically on how that applies when we're dealing with inverse trigonometric functions. Keep these pairings in mind, because we'll be putting this into practice with step-by-step examples on the next few slides. Recognizing these patterns is half the battle. Step-by-step procedure for substitution. Okay, so now that we've discussed what to look for, those key pairings of inverse trigonometric functions and their derivatives, let's solidify how to actually solve these integrals using substitution. This slide outlines a clear, step-by-step procedure. Step 1, identification. The very first thing you need to do when you see an integral with an inverse trigonometric function is to carefully scan the integrand. That's the function you're integrating, to see if the inverse trigonometric function is present. And crucially, check if its derivative is also present as a multiplying factor. Remember from the previous slides, we're looking for these packages, the function and its derivative together. Step 2, substitution. Once you've identified that pairing, the next step is to make a substitution. This is where we simplify the integral. We assign a new variable. We usually use t or u, but t is very common to the inverse trigonometric function. For example, let's say t equals arctangent of x, that is, t equals inverse tangent of x. This is the heart of the simplification process. Step 3, differential transformation. Now, this is a really important step that students sometimes miss. We need to express everything in terms of our new variable, t. To do that, we differentiate the substitution equation. So we differentiate both sides of the equation, t equals arctangent of x. With respect to x, this gives us the relationship between dt, the differential of t, and dx. And as we know from our derivative rules, the derivative of arctangent of x is 1 over 1 plus x squared. Therefore, dt equals 1 over 1 plus x squared dx. This equation is key to changing our variable of integration. Step 4, rewrite the integral. Now we rewrite the entire integral using our new variable t and the differential dt. We replace every instance of the original variable x and the differential dx with t and dt, respectively. This transforms the original, potentially complicated integral into a simpler one, hopefully one we can solve using standard integration techniques. Step 5, integration. With the integral now expressed in terms of t, we can perform the integration. We use our standard integration formulas, things like the power rule, the rules for integrating trigonometric functions, and so on. This is where your basic integration skills come into play. Step 6, back substitution. Finally, after we've integrated and have an expression in terms of t, we need to convert it back to the original variable x. We do this by substituting the original inverse trigonometric function back in for t. This gives us the final answer, expressed in terms of x, and don't forget to add the constant of integration, c, at the end. So these 6 steps, identification, substitution, differential transformation, rewriting the integral, integration, and back substitution, are the core of solving integrals involving inverse trigonometric functions. We'll see these steps in action with some worked examples on the next slides, so you can see exactly how it all comes together. Real-world context. These integrals with inverse trigonometric functions can sometimes seem a bit abstract, a little removed from everyday experience. However, they are absolutely essential tools in many real-world applications, particularly in fields like physics and engineering. Let me give you a specific example. Imagine an engineer is tasked with calculating the total work done to move an object along a curved path. Now, this isn't a simple straight-line movement. The path is curved, and crucially, the angle of inclination, how steep the path is changing as the object moves along it, relative to the distance traveled. In this kind of scenario, when the engineer sets up the integral to calculate the work done, it often involves inverse trigonometric functions. These functions help to establish the relationship between the linear distance the object travels along the curved path and the corresponding change in the angle of inclination. Essentially, they allow us to connect how far something moves with how much its orientation changes. Okay, let's move on to slide 4. Now, we've been focusing on how to do substitution with inverse trigonometric functions, learning to identify the function derivative pairs and perform the necessary steps. But it's important to understand why we're learning this. We'll be solidifying this technique with more examples on the next slides, but it's good to keep this broader context in mind. Knowing where these tools are used can really help motivate the learning process. Remember, mathematics isn't just about manipulating symbols, it's about solving real problems. Worked examples. Okay, let's move on to our first worked example. This will really solidify how we apply the substitution technique we just discussed. We're asked to evaluate the integral of tangent inverse of x divided by 1 plus x squared. With respect to x, that's written as integral of arctan x divided by 1 plus x squared, with dx at the end. Step 1, identify the pair. Now, remember what we talked about on the previous slides? The key is spotting that special pairing. Here, we have arctan x, which is our inverse trigonometric function, and we also see its derivative, which is 1 divided by 1 plus x squared. Both are present in the integrand, which is exactly what we're looking for. Step 2, substitute. So let's make our substitution. We'll let t equal arctan x. This is where we're simplifying the integral by replacing a more complex function with a simpler variable. Step 3, find the differential. Now, this is a crucial step. We need to find the relationship between dx and dt. To do that, we differentiate both sides of our substitution equation. T equals arctan x. With respect to x, the derivative of arctan x is 1 divided by 1 plus x squared. So we get dt over dx equals 1 divided by 1 plus x squared. To isolate dt, we simply multiply both sides by dx, giving us dt equals 1 divided by 1 plus x squared dx. Step 4, rewrite the integral. Now we can rewrite our original integral in terms of t and dt. Instead of arctan x, we write t, and instead of 1 divided by 1 plus x squared dx, we write dt. This transforms our integral into a much simpler form, the integral of t dt. Step 5, integrate. This is where the basic integration rules come in handy. Remember the power rule? The integral of t to the power of n dt is t to the power of n plus 1 divided by n plus 1 plus the constant of integration. In our case, we have the integral of t dt, which is the same as t to the power of 1 dt. Applying the power rule, we get t squared divided by 2 plus our constant of integration, which we'll call c. Step 6, back substitute. Finally, we need to get our answer back in terms of the original variable, x. We replace t with arctan x. This gives us arctan x squared divided by 2 plus c, and that's our final answer. So, to recap, we identified the correct substitution, found the differential, rewrote the integral, integrated, and then back substituted to get our answer. This example demonstrates the power of substitution with inverse trigonometric functions. We'll see another example on the next slide, building on these concepts. Worked examples continued. Okay, let's move on to our second worked example. This one builds on what we've already learned, showing how substitution works even when we have powers of the inverse trigonometric function. So, here we have the integral of quantity sin inverse x squared divided by square root of 1 minus x and x squared with respect to dx. Step 1, identify the pair. As we discussed earlier, the key is spotting that special relationship. In this case, we have sin inverse x, and if you recall from our earlier slides, the derivative of sin inverse x is 1 divided by square root of 1 minus x squared. Notice how that derivative appears directly in our integral. That's a great sign. Step 2, substitute. Now, let's make our substitution. We'll let t equal sin inverse x. This is where we're simplifying the integral by replacing a more complex function with a simple variable. Step 3, find the differential. Remember, we can't just change variables without accounting for it in the dx part of the integral. So, we need to find dt in terms of dx. If you differentiate both sides of our substitution equation, t equals sin inverse x, with respect to x, we get dt divided by dx equals 1 divided by square root of 1 minus x squared. Rearranging that, we get dt equals 1 divided by square root of 1 minus x squared dx. Step 4, rewrite the integral. Now the magic happens, we substitute. We replace sin inverse x with t, and we replace 1 divided by square root of 1 minus x squared dx with dt. This transforms our original integral into a much simpler form, the integral of t squared dt. See how much cleaner that is? We've turned a transcendental function into a basic power. Step 5, integrate. Now we can easily integrate. The integral of t squared dt is t cubed divided by 3 plus our constant of integration. See, remember your basic power rule. Step 6, back substitute. Almost there. The final step is to get our answer back in terms of x. We replace t with our original substitution, sin inverse x. So, our final answer is t cubed divided by 3 plus c, which becomes sin inverse x cubed divided by 3 plus c. And that's it. we've successfully used substitution with an inverse trigonometric function and a power. This example reinforces the importance of recognizing those derivative pairs and carefully handling the differential transformation. Now, let's move on to the next slide, where we'll summarize the key takeaways from this entire section. Key takeaways. First point, pattern recognition. The success of this entire technique really hinges on your ability to spot a specific pattern within the integral. What we're looking for is an inverse trigonometric function, like, for example, arctangent of x, and also its derivative. Remember from earlier slides, the derivative of arctangent of x is 1 over 1 plus x squared. If you see that pairing within the integral, that's a strong signal that substitution is the right approach. It's like recognizing a puzzle piece that fits perfectly. Next, simplification. The whole point of substitution isn't just to change the integral, it's to simplify it. We're taking a more complicated function, a transcendental function like arctangent of x, and transforming it into a much simpler algebraic variable, usually represented by t. This makes the integration process far more manageable, often reducing it to a simple power rule integration, as we saw in the examples on the previous slides. Finally, and this is crucial, the final step. Always remember to substitute the original function back into your result. After you've performed the integration with respect to t, you need to express your final answer in terms of the original variable, which is x. So, if you let t equal arctangent of x, you need to replace t with arctangent of x before you write down your final answer. The final answer must be in terms of x, not t. Okay, let's recap the key takeaways from using substitution with inverse trigonometric functions. This slide summarizes the most important things to remember as you practice these types of integrals, and it will help you avoid common pitfalls. Keep these 3 points in mind, and you'll be well on your way to mastering substitution with inverse trigonometric functions. Now, let's move on to the next slide, where we'll discuss some common mistakes to avoid. Common mistakes to avoid. 1. Confusing notation. The first and surprisingly frequent mistake is getting tripped up by notation. Remember that tan inverse x, or written mathematically as arctangent of x, is not the same as 1 divided by tan x. 1 is an inverse trigonometric function, it undoes the tangent function, and the other is simply the reciprocal of the tangent function, which is called cotangent x. Our substitution technique, as we've practiced, only works with the inverse trigonometric function. So, always double-check which tan to the power of -1 you're dealing with. 2. Ignoring the differential. Next, a very common error occurs during the substitution process itself. You correctly identify the inverse trigonometric function, say tan inverse x, and you set it equal to a new variable, let's say t. Great. But then, students often forget to also replace dx with its equivalent in terms of t. Remember, when we found the differential, we determined that dt is equal to 1 over 1 plus x squared multiplied by dx. You must make that replacement. You can't integrate with respect to dx when your integral is now expressed in terms of t. It's a crucial step. 3. Missing the constant. This is a classic integration mistake, not just limited to inverse trigonometric functions, but it's worth emphasizing. After you've performed the integration and simplified your expression, always remember to add the constant of integration. C. The derivative of a constant is 0, so it gets lost when we differentiate, but it's essential to include it when we're finding the indefinite integral. 4. Sign errors. Finally, let's talk about cos inverse x, or arc cosine of x. The derivative of cos inverse x is -1 over the square root of 1 minus x squared. It's easy to forget that negative sign. When you're doing your substitution, make sure you carry that negative sign along correctly. A missed negative sign can completely change your answer, so pay close attention to it, especially when dealing with cos inverse x. Okay, let's move on to the final slide, which highlights some common mistakes students make when tackling these substitution problems with inverse trigonometric functions. Paying attention to these will really help you solidify your understanding and avoid losing marks in your exams. So, those are the key pitfalls to avoid. Keep these in mind as you practice, and you'll be well on your way to mastering substitution with inverse trigonometric functions. Remember to review the worked examples we covered earlier if you need a refresher on the correct procedure.